Good afternoon, everyone. My name is Junhua Yan, and my presentation today is about feature selection in website fingerprinting. This work is done with my advisor, Professor Justin Core from UNC Chapel Hill. Website fingerprinting aims at determining the visited website by inspecting network traffic on client side. So it has, it has a wide range of applications and is relevant to a lot of network entities, such as network managers, internet service providers, or even malicious entities who want to use private user data. So in a classic attack scenario, an observer usually resides in the first link that connects the client and the internet. So when a client is opening a website, all traffic going through that link will be captured by the observer for feature analysis. So there are two commonly used methodologies nowadays for website fingerprinting. The first one is deep packet inspection, which looks at the payload of each IP packet. And the second approach is TCP/IP signature-based identification, which focuses on extract features from TCP/IP headers and then use supervised machine learning algorithms for classification. So our work will focus on the second approach. And in the past decade, the second approach has been the main approach used in the field of traffic analysis because it's due to its generality and good performance. And researchers looked at different communication scenarios which differ from each other in terms of the availability of information in TCP/IP header. For example, the most popular scenario studied nowadays is Tor, in which only the packet direction and the timestamp is available. And in each communication scenario, they looked at different types of features, and they also experiment with different machine learning algorithms. Although the results they obtained is promising, their work are limited in the set of features studied. For example, the most commonly used feature in SSH is packet size count, while in Tor is number packets. So with limited features, it's hard for us to understand what is the extent of website fingerprintability. So what do I mean by extent here? As an attacker, I want to know what's the best accuracy I'm able to get with all the information available from TCP/IP header. And as a client or server, I want to know what features are most informative so I can work on hiding it to protect my privacy. So in order to understand that, our work focuses on perform a relative exhaustive feature selection with all information that are available in TCP/IP headers. So we start with three questions. Are there other features that can be used to achieve comparable accuracy with state-of-the-art? What if we hide some of informative features that has been discovered before? Can features that are informative in one scenario be used to accurately identify websites in another scenario? And to answer these questions, we extract a comprehensive list of TCP/IP header features. We consider 8 different communication scenarios, and in each scenario, we identify and analyze the importance of features we extracted. So let's first talk about the features we extract in this work. Remember, our goal is to do a relative exhaustive feature selection, so we need to have as many features as possible. And in order to achieve that goal, we organize our feature extraction process in a hierarchical way and extract features from 5 levels. Packet level, which focuses on individual packets. Burst level, for burst information in one TCP connection. And TCP level, port level, and IP address level. And furthermore, in each level, we categorize those features according to their semantic meanings. For example, features about number of incoming packets belong to one category, while features about packet size count belong to another category. So in total, we extract 109 different feature categories across these 5 levels, with a total number around 36,000 features, and 61 of them has never been considered before, such as the total transmitted bytes with regard to port 443, or the size and direction information about the initial bursts. So next, I'll talk about the communication scenarios we considered in this work. So we start with HTTPX, which includes HTTPS, HTTP1 and 2, And in this scenario, no additional privacy-enhanced technologies are applied, so all information in TCP/IP header are available. And then we hide the IP address. Things for some network entities, they are not able to access the IP address information. And then we looked into encrypted tunnels, such as SSH and VPN, when packets from different TCP connections are multiplexed due to the proxy server. And the next, we consider two scenarios with fixed packet size, because packet size has been proved to be the most informative features. HTTPX with patch UMTU and Tor. So in Tor, the only available information is packet direction and packet time. And based on Tor, we further hide the timestamp of each packet. In the last two scenarios, we consider unidirectional packets because incoming and outgoing packets may be routed through different links. So compared with previous work, most of previous work focused on Tor, and some of them focus on encrypted tunnel, SSH VPN, and only a few of them looks at HTTPX. So compared with their work, we consider more possible scenarios by considering both the privacy-enhanced technologies and also the countermeasures proposed in previous research. So having determined the features and the communication scenarios, our next goal is to perform feature selection to select informative features in each scenario. And to measure the importance of each feature, the criterion we use here is the mean decrease in purity importance derived from decision tree-based ensemble math, such as X tree or random forest. MDI importance has been widely used in gene selection, so I won't give details here, but we can discuss later if you are interested. So the key idea is to compute the average decrease of entropy of each feature in multiple decision trees to measure their importance. Thus, the higher the MDI importance, the more informative the feature is. However, one potential issue with MDI importance is it is biased with correlated features. So what does that mean? Suppose we have three unrelated features, trace duration, incoming bytes, and number packets, and their MDI importance is 0.3, 0.3, and 0.4. And if we add one more feature, total bytes, and suppose we are transmitting our packets in a fixed size, so in that case, total bytes and number packets will be correlated with each other. And the MDI importance of number packets may be decreased from 0.4 to 0.2. So in this case, if we are required to select two most informative features, we end up with trace duration and incoming bytes instead of number packets, although it's more informative than the other two. So one possible solution for this problem is to first cluster coordinated features and then choose one from each cluster as a representative before we calculate their MDI importance. However, the computation complexity for calculating the correlation between each pair of features is O(n) squared, where in our case, n can be as large as 36,000. So computation efficiency is another thing we need to consider in this project. So after taking both the bias and the computation efficiency into consideration, we finalize our feature selection methodology into 3 steps. So we start with a feature set that contains both irrelevant and correlated features, and our first goal is to reduce the number of features to reduce the correlation computation. To do that, we first calculate the MDI importance of each individual features and consider only top n features that contribute to 99% of the total MDI importance. And by doing that, we greatly reduce the number of features for future analysis by filtering out those less important ones. And so our feature set contains only relevant and correlated features right now. So the next step is to remove correlation. And we use hierarchical clustering based on Euclidean distance to measure their correlation. And to determine the optimal number of clusters, we use silhouette score. And the score is defined as the ratio of average distance between samples in a cluster across different clusters to the average distance of samples within a cluster. So the higher the score, the better our clustering scheme is. And then we select one feature from each cluster for consideration. So until now, our feature set contains only relevant and uncorrelated features. So we recalculate MDI importance again and rank the importance of those features after grouping features with the similar semantic meanings we defined before. So in each communication scenarios, we use this feature selection methodology and rank the importance of features. So before I talk about our evaluation, let's look at our data set. For feature selection, we collect the data sets by visiting 3,000 top 3,000 websites listed in Elixir each 20 times with Chrome. And after ruling out unsuccessful visits and taking redirection into consideration, we end up with around 2,000 websites, each with at least 16 visits. And we also used other public data sets that's collected in different communication scenarios for performance evaluation. SSH 2000 web datasets collected over SSH and two Tor datasets collected over Tor browser. And with those datasets, we first select informative features in each scenario, and then we compare the classification accuracy with feature set proposed in previous research in both the closed world scenario, open world scenario, and in face of different countermeasures. So due to time limitation, I will briefly talk about our results in Tor scenario, in which only packet direction and timestamp is available. And we identified 38 different feature categories and ranked them according to their importance. And 50 of them have never been considered before, and they contribute a total MDI importance around 22 out of 100. And for example, one informative feature we found is cumulative packet size with direction, which calculate the sum of packet size that has been seen before a current packet. And the reason why this feature is important is because it's further exploits the incoming and outgoing packet ordering. So for classification, for performance evaluation, we use features identified by us and 8 different feature sets proposed in previous research. And to control the variation brought by different machine learning algorithms, we use extra tree on top of each feature set and get the final result with tenfold validation. For example, if we use 2,000 websites from our datasets, we outperform the state-of-the-art around 14%. And with SH 2000, the gap is further increased to around 17%. And we observed the consistent performance in all, across 8 different communication scenarios. And so, in conclusion, in this project, we extract a comprehensive list of features from TCP/IP header for website fingerprinting, and we study 8 different communication scenarios. And in each scenario, we identify and select informative features and rank them according to their importance. So, in the future, we plan to consider some practical issues in this field, such as the impact of caching, the geographic location, and the different client browser platform. And also, for now, we only consider single-tab browsing. If we instead consider multi-tab browsing, how will the performance of website fingerprinting decrease? Or thank you.
Do we have questions?
So I was just wondering a little bit about how you controlled for overfitting, where so you have you're evaluating your feature set on your data set, but you also used your data set to do the feature importance, or did you segment it so that there was a separate data set that was done to figure out the important features? Because otherwise, it's possible that that's sort of focused on your data set, right?
Yes, that's one possibility. So we used actual data set for performance evaluation also, because the scale of our data set is a little bit small after ruling out those unsuccessful visits, and the data collection is a time-consuming process. So instead of separate them, we used other public data sets for evaluation to validate our performance.
Hi, good talk. I was just wondering, like, you used a methodology that seems to come from like many other, like another area, say, not specifically to website fingerprinting or networking. So can you say a little bit about like how much you think there's value to having some domain knowledge being applied to when you pick the features, or can you just, doesn't matter, you don't need to know anything about networking, you can just use this methodology and it'll give you the features that you need?
So the methodology I use here, the MDI, I'm asking about MDI importance. The methodology I use here has been widely used in other fields, but the particular issue in this project is the bias. For example, in gene selection, they just want to select a group of features that works best to serve their purpose. But in our project, we also want to rank the feature according to their importance. So maybe bias is not a problem in this project, but it's a problem in our project. So it's like the same methodology, but we have different concerns, so we are trying to solve this problem to make it work.
Hi, I saw that you used the TCP port, or you checked how useful the ports would be for website fingerprinting. Could you give what's the intuition for that, or how that would be helpful?
The intuition is, so when the TCP connection information is available, so it may serve from HTTP or HTTPS, and for HTTPS, it's served over port 443, and for HTTP, it's served over port 80. So that's the intuition. We want to see the portion of traffic that's served by HTTPS and HTTP when visiting a website.
So I saw you cited in your slides the paper by Rimmer et al. At NDSS that appeared earlier this year that was using deep learning. Where they emphasize on the fact that by using deep learning, they're able to do website fingerprinting without feature engineering.
Yes.
Could you comment on the impact of that relative to the findings of your work?
Yeah, deep learning is a good direction to go, and we don't need feature engineering. But for countermeasures, it's important for us to develop efficient countermeasures if we have the information about which features are most informative. And the second thing about deep learning is, in order to train the model, we need to a lot of samples for training, and that will be time consuming. And when we collect the data set, we need to, so the data collection is time consuming because we cannot run multiple, we cannot visit multiple websites simultaneously, so it has been one website after another. So I think samples and the important features are the two.
Okay, let's thank Junhua again.